So, thanks very much for coming. My name's Kieran Bowen, and I work on the 3D team at Neftex. I recently had a bit of a croaky voice, so I apologise if I cough and stuff at any point. What I want to show really is what we've learned at Neftex from doing regional mapping, and in particular what we've learned from doing this in DecisionSpace, which we've been doing since July when we were acquired by Halliburton. The talk is on continental scale mapping in DecisionSpace, and I'm going to use the Central American region as an example. To give an outline of the presentation, I'm going to give an introduction to Neftex. This is who we are and what we do. Then I'm going to talk about some of the challenges that the industry is faced with today, and hopefully in the rest of the presentation I'll be able to address some of these. Then I'm going to talk about the 3D vision, and this is really what we're working towards within Neftex, and in particular the 3D team. And then the bulk of the presentation is a video demonstration of regional mapping techniques and basin screening. I'll quickly mention some of the next steps at Neftex, and then I'll wrap up at the end. So, Neftex was founded in 2001. We're a consultancy consisting of about 120 staff with a very high proportion of geoscientists. All these geoscientists reside under the same roof on an open floor office plan, so we can all go and talk to each other within a 20-second walk. So the point is, we have geoscience really at the heart of everything we do. And what we're working towards, or what we do, is we're building this global Earth model, a 4D global Earth model. And the idea is we have clients who can subscribe to it, and these include super majors as well as smaller companies, and they can gain various tools and products from this Earth model that they have access to aid their exploration effort. We also have a smaller consultancy division. This consultancy division acts more like the traditional sense of a consultancy, as in they'll take proprietary data from a company and use similar workflows and processes to work it up and aid that company's interpretations. So this slide best summarises what it is we do. So up here, this cloud at the top, I'm not sure if my laser pointer works on it. So this cloud at the top here represents publicly available data. And what we do is we collect as much of it as we can, and we catalogue it. And this can be anything from seismic to geochemistry to well data, biostrat, geological maps, literally anything that can aid exploration, we'll capture and we'll catalogue it. That then goes into this funnel here in the middle, and at this point it's interpreted with a sequence stratigraphic framework. What this means is we can take all this data that has different naming conventions, that comes from different countries, different disciplines, and make it all speak the same stratigraphic language, so that we can use it, we can correlate it with one another. So we can take an outcrop from China and correlate it with an offshore well in Nova Scotia or wherever. So once we have this in place, we can then build a set of products and tools such as a geodynamic model, gross deposition environment map, clay cross-sections, chronostratigraphic charts, a number of other useful things that basically can help us explore. So this is the data we're working with. This is what we have. So we have a well and outcrop database of about 17,000 wells. And then in the top right, you can this basically just shows that we're constantly updating this, so we know we have up-to-date data. We also have a petroleum systems, which is a geochemistry database, and a reservoir seal database. The key things about these is they all sit within that same stratigraphic framework, so all this data speaks to each other and we can use it all globally. So I just want to spend a little bit of time talking about some of the challenges we're faced with, and then hopefully address these in a bit. So if I draw your attention to that box in the bottom right, challenges and regional techniques, the first point here is vast and disparate data. So how do we cope with it? Publicly available, you can get huge data sets. You can get online databases from USGS, you can have dusty old maps sitting in a library somewhere. We need to be able to collect this and use it and make it accessible. But we also need to use it in conjunction with our own data and every different type of data that we can get our hands on, really. So this is one of the things we'd quite like to address. Secondly, knowledge preservation. This is kind of related to the first point. If we have this vast amount of data which is always coming in, interpretations need to be updated and models need to be rerun. And every time this happens, we need to document this. So if there's a new geoscientist entering a company, they can immediately learn the reasons behind these interpretations that another geoscientist has made. And if you couple that with the fact that we have the crew change impending, or happening now, then it's even more valuable to capture all this knowledge that the more experienced members of staff going to leave behind. New ideas from old data. So considering how few large discoveries are being made at the moment, and this is the end of easy oil with tighter margins, higher costs, and accumulations which are getting harder to find and harder to develop, we need to nurture these new ideas because they're going to become more valuable. So how can we do that, and how can we do that with regards to old data? And then the last point is evolving interpretation. This, again, is similar to the first point. If we have all these interpretations which are updated, maps that are redrawn, models we run, we need to make this process as automatically and as efficiently updatable as we can. So any steps we can do towards that are going to be highly beneficial. So with that last point in mind, this slide shows a generic workflow, a static generic workflow that someone in the oil and gas industry could adopt, and there will be variations of it. So in this example, you start with some data. So here we have some well data. That's going to be interpreted by a geoscientist, and that will sit within some sort of stratigraphic framework, probably with its own nomenclature. Here that's represented by the chronostratigraphic channel. Then perhaps the geoscientist will draw a gross deposition or environment map, and that's what you're seeing there. And then maybe they'll talk to the geochemist, or maybe they'll switch software package and look at some maturity data, and then draw a petroleum systems map. Whatever variation of this workflow, ultimately, often you're going to end up in a common lift segment map. Now this workflow, it works, and it's fine, but the issues with it are, if something changes up here, if this well interpretation changes, or there's new data, this doesn't echo through, so this map needs to be redrawn, and so does that map. And every time you redraw a map, it's basically out of date immediately, because you've always got new data coming in. So if we can take any steps towards automating this process, it's going to be hugely useful. And on top of that, considering you often have multiple people contributing to this, and often multiple software packages, if you can condense it into one software package and make it available to all the people involved, then again, it's something we want to work towards. So that brings me quite nicely to the 3D vision, or the shared Earth model. And this is basically an idea or a concept that we're working towards. This is the ultimate goal that we want to achieve in the 3D team at Neftex. And the idea is you take all your data that you can get your hands on from as many different disciplines, many different data types, all residing in the same place. But it's not just a database, it's a model, so it also has interpretations. So here you can see some maps and charts and whatnot. So the idea is you put data in, interpretations update themselves, and you can take outputs out, and occasionally feed that back into the model. So an example of this might be, let's say you have a geodynamic model and you do a plate reconstruction. Maybe you draw a gross deposition or environment map based on that reconstruction. Let's say you get some new data in, new well data, and you use the biostrat in your model to correlate it, calibrate it, sorry. Now, let's say that actually tells you that there's some sand where your gross deposition environment maps didn't originally depict the sand. Those maps will then update, and then suddenly you might have a new play concept or idea that you've got as an output from the model. So that's what we're working towards. And if we can have this in the same workstation, accessed by multiple users, then we've done our jobs. So this slide is just to sort of reiterate that we have quite a lot of experience of working regionally in 3D. So we've used a number of different software packages, got over a number of different software and hardware sort of hurdles. But the points I want you to keep in mind are that we've worked primarily regionally. We do some basic models as well, but a lot of the work we do is regional. As well as that, as you can see in the top right picture, we have the ability to work with geological time as a z-axis. So here we're not looking at two-way time, and we're not looking at true vertical depth. This is a little bit different. This leads me on to the video demonstration, which hopefully works. So it looks like it's working. Hopefully the first thing you notice is the scale. Yes, red box is our area of interest, and that's obviously the whole of the Central American region. So the first thing I want to demonstrate is the types of data we can put into the software. So basically anything that could aid regional mapping, that could help basin screening. So here you see regional faults, regional folds, tectonic elements, and all of this is done and worked on with the geoscientists in-house. You can also put in any cultural data you might want. So here we have a digital elevation model, coastline, license blocks, cities, whatever it is you can think of, anything that can go in GIS effectively, GIS. So, what you're seeing at the moment is an array of play cross-sections. what these are, they're basically a synthesis of publicly available data to create a summary of a basin in the form of a cross-section. And these are really useful for immediately gaining an idea of the structure and the stratigraphy of a basin. On top of that, they also have all the proven plays listed as well as conceptual plays listed. And a way you might use them is to quickly learn about a basin and to try to generate ideas. So these are in depth. And let's say you had a carbonate play you knew about in one basin, in say the Cretaceous, and you wanted to see if there's a viable play in a neighbouring basin. That might be one way you might use them. So again, sticking in the depth domain, these are all those wells. I showed some wells on a slide earlier. These are the ones that fit within this AOI, and all of these are publicly available. Wherever possible, we can provide the log traces, but that depends on permission. If not possible, we'll always be able to provide these sequence stratigraphic pics. And this is what I was talking about before, with all these wells and different data types speaking the same stratigraphic language. With all these data pics in on every well, it means we can correlate all the wells across the entire region. With that in mind, here we switch to a log correlation view. And a lot of geologists will be familiar with this sort of thing. Here you can do a lot of the things you would expect to be able to do, like move sequence picks up and down, use log trace tools and show the traces and whatnot. And all of this sits in the OpenWorks database. So the OpenWorks database sits behind DecisionSpace, and that basically reads from it. And because it does that, it means you can attribute these sequence picks. So you can give them fasces and confidence. And giving these things confidence is actually really valuable when working regionally, because you have such varied data sets. Now, something that seems quite simple at first, something we've always struggled with, is embedding hyperlinks into the software. This is really valuable because it means you can take a well and go, why was the well picked like that? So with 2 clicks, it takes you straight to a PDF that's attached to the website. You can see all the biostrat and all the log trace information, and basically everything that those wells were interpreted on. The idea is we're making every interpretation we make as transparent as possible and as accessible as possible. And obviously that's a hugely useful tool. Now, there's been a big sort of switch. We were just working in the depth domain, but now we've switched to geological time as the Z-axis. So you can see that here we've got some chronostratigraphic charts, and they have the time scale along their Z-axis. Once we have these in the software, we'll basically build the skeleton of a chronocube with these charts. We can then slot in gross depositional environment maps along sequence boundaries and maximum flooding surfaces. Now let me remind you, these are flat because we're in geological time. So these maps are all deposited at the same time, which is why they're coming in flat. So they're brought in as attributed surfaces, so they're not just images, which means they're fully queryable. And once they're slotted in, it means you can zoom in and interrogate certain parts of the region. This is useful for learning about that part of the region, and it's also useful for figuring out busts, because that does happen. Now, every map that's brought in, by definition, is an interpretation, because it's drawn by a geoscientist. And same with the charts. So every time they draw these maps, they document all their reasons for drawing polygons in certain ways, and every interpretation that goes into that map. So as you can see, there's a lot of notes that have been documented by our geoscientists in-house. So we can import all of these notes into the OpenWorks database, and they're spatially enabled, which means they've got an X, they've got a Y, and they've got a Z. In this instance, Z is geological time. And what that means is we can instantly attribute those particular notes to the map in question. So I think this is the Wilcox map, which you can see in the Gulf of Mexico at the top there. So we might want to query, why those turbolite sands were drawn that way. And that's something we can do easily now. Before, what we'd have to do is identify which map we're looking at, go to the Neftex website, put in your client login details, identify the map in the website, open the PDF, scroll down to the correct note. Now it's a lot more simple. You just click on that note. The note written by the geoscientist immediately comes up. From there, there's a hyperlink which takes you straight to the Earth Search database website. This is the database we use to catalogue all our publicly available data that we've read or used. That has full bibliographic information, and then a link that takes you straight to the source of the data. So in most cases, it's going to be the publisher's website, which takes you straight to the page of that paper or particular journal or whatever that note was based on. So again, this is trying to make our interpretations as accessible and as transparent as we can possibly make them. So far, everything we've looked at is just basically visualizing data and interpretations of maps and charts in 3D. What we want to really be able to do is methodically use this to tell us something about exploration. So as I mentioned before, all those gross deposition environment maps are slotted in, and they're brought in as attributed surfaces, not images. That means we can use this attributed data to fill a model and create a geocellular model between all our sequence boundaries and maximum floods. What this means is we end up with this geocellular model which we can click anywhere in time and space in that region and get a good idea about the depositional environment and the fascia. It's a really useful way about learning about a part of the region. And then you can use various interrogation tools like creating these sections through it, and that basically creates a new chronostratigraphic chart for wherever you want in the model. So again, it's just a good way of learning about that part of the region. Now, as I've said for like 2 or 3 times now, everything's attributed. That means we can start to build queries which help us zone in on things we're interested in. So in this example, we've queried out anything that doesn't have potential for organic enrichment and left behind those green polygons. Here they've done it for reservoir fascies, so basically, deep marine shales are now gone from that part of the model. Whatever query you want to build, it's entirely at the user's discretion. So if you're only interested in the Custrian source rocks, you can just do that. If you're only interested in Cretaceous rocks, you can do that. And that applies for both, reservoir, source and seal. You'll see our seal query is actually quite optimistic. Now, let me remind you that these queries that we're showing on the screen here are all through geological time. So when it switches to map view, which it's about to do, you're going to see some polygons. So these are the organic enrichment polygons, and that's all through geological time. And what you can do is you can then stack the reservoir polygons on top of that, and the seal polygons on top of that, and then when they juxtapose, if you click the polygons in that way, you've basically got a basin screening map. Now, this is pretty useful because it means it's done automatically, and as I mentioned, the seals are quite optimistic. So, because it's done, basically, if you have the Chronicube and you have all these maps which result in these basin screening maps, if these maps change, you don't have to redraw these basin screening maps. That's the value. They immediately update themselves, and whatever query you want, you can do it that way. You can then sense check these by putting in regional oil fields and regional gas fields, just to show that it makes sense. Now, so far, we've been working strictly in the geological time domain, and basically we've been looking at first-order depositional controls to learn about a region, interrogate a region, and provide a first-pass basin screening. But we know there's a lot more information in the public domain that we can utilize to further constrain these interpretations. So what you're seeing at the moment is a lot of images that have been clipped from papers and journals and whatnot that have been imported into the software. So what we do is we georeference the location maps, import those, and then drape these images from them. These images can consist of anything from structural cross-sections, depth-converted seismic lines, sections created from geologists in the field, whatever it is that gives an idea of depth geometries. And they don't just have to be images, we can bring in isopacks or whatever it is, anything that helps us get an idea of depth. You can then interpret these in a similar way you might interpret a seismic line with it coming up in the section view. And once you've done this, you gain a pretty good understanding of the depth patterns over the entire region. And on top of that, you saw the wells that we had available to us before. You can add those well tops to that to constrain your surfaces. So what you've got here is a publicly available regional digital elevation model. This can also help constrain these surfaces. Pardon me. So the surfaces we choose are based on data availability as well as petroleum significance. So here we have a base tertiary surface, and that was selected partly because of its proximity to the Wilcox. And then here, the top paleogene. So in this instance, you can see some of the salt structures in the Gulf of Mexico. Now, because all of this is in depth, it means we can make some assumptions. So let's say we have some reservoir seal data, which is what we have here, and that suggests that beyond a certain depth, all the reservoir rocks in this part of the region are ineffective, they're buried too deep. So we can provide a cutoff so the polygon no longer shows that. And that further constrains these basin screening maps a bit more. You could also do a similar thing for source rocks. So if you have maturity data, pitch and reflectance, or whatever it is, you could do that query instead. Now, this section of the video is the dynamic frameworks to fill basically workflow. And it really documents how we make these surfaces. So what you're seeing here is a high resolution grid in the Burgle Basin added to a framework. And the framework is the tool we use to build these surfaces. What just happened there was it took all that data from those vertical images and added it to the same framework. Instantly the map updated, and which is why it now covers most of the region, and it's drawn a depth map of the region. What you're seeing now is it's taken all the well data, all those sequence stratigraphic pics which are imported as well tops, can now be added to the same framework and instantly updates itself in real time. Hopefully you can see the advantages of this. If you get a new piece of data, it goes in the inventory, and then a couple of clicks, you've updated your depth maps immediately without having to rerun processes or redraw them. And that's one of the advantages we want to stress here. So here you can then change the resolution. Obviously we have quite a low resolution here, and that will probably depend on your data density and quality. And if you want to bring in time data, as long as you have a velocity model, you could do that. What you can do is it's multi-user. So I don't know if it's happened yet because the video is a bit ahead of me. No, here we go. You can take an interpretation that another user has made from a different workstation and add it to the same framework. So basically you have multiple users building the same maps. Now, because we're working regionally, and because we're building multiple surfaces, there are inherently going to be mistakes and busts. There's going to be areas where you don't have data, and there's going to be areas where the data is rubbish. So there's a certain set of things we can do to sort of guide this. Once you build all these surfaces, there's going to be areas where one surface might go above a regional unconformity, or might go above the digital elevation model, or below the depth of basement map. When this happens, you know there's mistakes. So, and I think you're about to see it here, as we add more surfaces to the screen, it gets jumbled up and it turns into a bit of a mess. So you can apply certain geological and stratigraphic rules to the framework, and that makes these surfaces abide by these rules that we know to be true. So what it's about to do here is take the digital elevation model and select it as an unconformity. What that means is, if any surface goes above it, or attempts to go above it, it will get truncated. So that's what's going on there. If you do this for regional unconformities as well as digital elevation models and whatever surfaces you see fit, you're immediately going to get truncation patterns. And there are tools you can use as well to perhaps guide a surface using another surface that does have data when you're short of data. Once you've applied all these rules, and then you can colour them up in all these very cartoony colours, and then immediately you can see outcrop and subcrop patterns because all these surfaces are being truncated by unconformities and the digital elevation model. And that basically allows you to see sediment packages which belong to tectonic mega sequences or whatever it is you've mapped originally. And this is a really valuable tool to use when you're doing any sort of regional mapping. That's the end of the video presentation. Hopefully I've stressed enough the importance of having this dynamic updatability and how valuable we find it to be while doing regional maps. And just to finish off, I've got one slide on our next steps, namely Permedia, and then 2 slides to conclude. So Permedia is basically a basin and petroleum systems modelling package, and it goes 1D through to 4D. We've done a little bit of experimentation here in 1D on our Burgess Basin study, but you're going to see a lot more development and experimentation in the near future, and you'll see this with our 3D basin scale models. So it'll be interesting to see what happens there, so watch this space for that. And then just to conclude, what can we do with vast and ostensibly disparate data sets? If we can have it all in the same place, that's excellent, that's something that's very beneficial. And by having a sequence stratigraphic framework, it allows us to take globally inconsistent data and correlate it with one another and use it. Hopefully that's demonstrated in some of what I've shown. Knowledge preservation, hopefully I've shown here that by embedding hyperlinks and adding spatially enabled nodes, we're making every interpretation we make very easily accessible, and the whole sort of process as transparent as possible. Ideally we want everyone to adopt this sort of approach, and it's just a case of actually doing the documentation in the first place. So this is really in place already. Now, hopefully with the dynamic frameworks to fill, the end bit of the video, I showed that the map building process is getting more efficient and it's becoming automated. And as well as the basin screening exercise with these chronocubes, if these maps update, then so do the basin screening maps, and you don't have to redraw them. So things are starting to get more automated. That workflow I showed at the beginning, there are sections which are still static, but this is improving. So we like to think that if you're working on a postage stamp bit of 3D survey, and you have the ability to zoom out and instantly get a regional understanding of the area you're working in, you've got all the publicly available data, you've got the legacy data, and perhaps you've got data from different disciplines that you wouldn't normally look at. This is the platform we think you want to be standing on if you're going to come up with new ideas. And with that in mind, hopefully your interpretations and your decision making will be better for it. And that's the end. Thanks for listening. Any questions?
Thanks, Kieran. Well, let me ask you, because I've known Neftex quite well for a number of years. What you didn't say is that if you'd given this presentation a year ago, you'd have been using a different software system.
That's quite right.
Petrel.
Yeah.
And back in June or July, that sort of time.
Yeah, June, I think.
Petrel went, and you brought in Landmark, and it seems to me one. I wouldn't hear from Neftex again for about 2 years while you absorbed this new software. It seems more like 2 months. So it's obviously been a relatively straightforward transition. And it seems to me also that you're doing more than you would have a year ago. Are those two things fair?
Partly. So you're right, we did dive in head first the moment we got our hands on DecisionSpace. And something worth noting is that everything we did before in Petrel, we still deliver. You can still access it, anyone who subscribes to it still gets it. But the main focus is basically all development is now switched to DecisionSpace. There are some things that fit better. So as I mentioned, DecisionSpace has OpenWorks sitting behind it. This is a database that DecisionSpace reads from. And this is partly very beneficial for us because we have lots of data, vast amounts of data, and it sits within databases. So we can put it in OpenWorks and just view it and have multiple people viewing it. And this is bread and butter, this is what we want to hear. But the OpenWorks database is also a little bit inflexible, so that there is some teething pain with switching to DecisionSpace. But there are definitely elements which we love. The dynamic updatability, considering how much data we have and how often it's updated, we need to be able to update efficiently. So from some aspects it's very good. But there might be some aspects as well that will change, and perhaps things in Petrel that we were developing might not be developed quite as much now.
Okay. Anybody got any questions? Yeah, please, Chris, just wait for the microphone. And I know perfectly well who you are, but it'd be good to say who you are and where you come from.
Chris Walker, Fairfield Middle. Very impressive, very comprehensive, at least for the Gulf of Mexico examples you showed. What about areas where data access is notoriously difficult, like the Middle East, Saudi Arabia, etc., etc.? How do you cope with areas like that?
So that's a good question. Data availability is always an issue for us. And we haven't actually done this yet in the Middle East, so we're going to work around all the various regions. But basically, it's the exact same approach. If we don't have data in a region, the first thing we do is look for the data in that region. Failing that, there are various other techniques we might be able to use. So you can use surfaces that do have good data constraint to guide other surfaces, for example. Whenever things like that are done, we try to avoid it. We'll annotate it as best we can, because ultimately sometimes these things are interpretations. So you'll see in the notes and all that where that's documented. But basically it's the same workflow. We just have to do our best. And we have teams of people where we'll have a day where we'll blitz the research and everyone will dip their hands in. But it's much the same workflow. We have to do our best, and we document it every time we have poor data coverage.
Okay, yeah, Ian.
Yeah, hello, Ian Jack, mostly retired Just a question. I did see a paper at the EAG this year by Statoil, which seemed to imply that, as well as this, they had all the seismic data in the database as well. So, would you comment on that?
By they, do you mean them or us?
I don't know. Statoil gave the paper.
Okay. So, with regards to seismic data, everything we use is publicly available. So I can't speak for Statoil, but we have a large amount of seismic data in certain regions. So, Geoscience of Australia obviously give out large amounts of seismic data, and we regularly use that in anything. So here you're looking at the Australian one. That would be used for that.
Okay, no, I just noticed that there seemed to be very little in the way of seismic in your presentation.
Yeah, so it's basically region dependent. Sometimes there will be next to none, sometimes it'll be entirely based on seismic. Some of our basin scale models are entirely based on seismic.
Thank you.
Okay, anybody else? All right, thank you, Kieran.
Thanks very much.